implicit differentiation is maybe one of the scarier looking things that we'll see in this class, but it's really not too bad. Now, what we're mostly dealing with is explicit functions, where we can put y on one side and our x variables on the other side. With implicit function, we've got maybe something like a constant is equal to some function of x and y. Now, in this case, we've got this equation. We've got some mathematical logic tying these variables together. And so implicitly, if we change x, we're going to have some change in y to maintain that equality. So in effect, we're saying we've got some function of x, and then y is implicitly its own function of x. So that's what we mean when we say implicit. So let's go ahead and walk through an example, and I'll explain what's going on as we go. So let's say 4x squared minus y cubed minus 97. Now, you might be tempted to just say, well, let's move the y over, equals 97. Let's move the y over, let's subtract 97 from both sides. We can take the cube root of the whole thing, and we can find the explicit derivative. We're going to take a slightly different approach here. We're going to leave the y over on this side. Now, this method is going to be really important if we've got something like, say, x times y. So if we have, say, a Cobb-Douglas production function, we might say something like q equals alpha to the labor to the power of, let's say, beta times capital to 1 minus beta. So in that case, you're going to have some constant level of quantity being described by some mix of labor and capital. And so this function looks something like this, and we want to know what is dk dl. Right? We want to know what is the slope at some given point on this function. But in this case, we're not going to be able to disentangle k and l as easily. All right, so let's jump back to here. First thing we're going to do is we're going to set this up like we're taking the derivative, really the whole thing. Right? So what's d dx for 4x squared? Well, that's just the derivative the normal way. That's just going to be 8x. For 97, how much does this change as we change x? Well, the answer is 0. Here is the tricky part. So I'm going to call this d dx of y cubed. So we still haven't solved it yet. So what we're going to do with this is we're essentially dealing with a chain rule situation. So when I say y cubed, effectively what I'm saying is d dx of some function, let's call it y of x cubed, which means now I'm in a world of chain rule. All right, so what do I do with this? Well, I take 3 times y, which is a function of x implicitly, and then I multiply that by y prime. All right, so that's how, this is really all it is, right? It's almost like a trick. So let's go ahead and introduce that down to here. We've still got 8x minus, now we've got 3y squared. Whoops, I forgot that over here. Let's pretend like that didn't happen. 8x minus 3y squared times dy dx equals 0. And then we just solve for dy dx. So that is dy dx equals minus 8x divided by minus 3y squared equals 8x over y squared. So the exact slope is going to depend on where we are in terms of x and y. Now, if we've got a setup like this, when we change x, we're only going to have certain, or say change L, we're only going to have certain values of k that are going to be consistent with the underlying equation. Right? So again, y is implicitly a function of x, or k is implicitly a function of L, if we're using those terms. But given that, we can plug in some specific value and then we can find what is the slope at that point. All right, so that's really all it is. It's relatively straightforward. Now, you'll see more explanations, we'll do more examples, and you'll get more comfortable with this. But really, all we're doing is we're recognizing y as implicitly a function of x, and we're doing some chain rule, and that lets us jump right down to here. We move the exponent down, we say 3y squared, and then the derivative of the thing that we're raising to the power of 3, which is just dy dx. Cool.